Let's wrap up this lesson by reminding you of how to rationalize the denominator. We said that a radical is simplified when there's no perfect factors in the radicand, but also you can have any radicals in the denominator. So something like this is not simplified. So let's remind you of how we simplified when we dealt with square roots. So the first thing we did was, I already said, pull it apart like taffy. Use your quotient rule. This is equivalent to the root of 2 over the square root of 5. And I need to get rid of the square root of 5 in the denominator. So what was my trick before? Well, I multiplied by what was in the denominator before to make the bottom be the square root of 5 squared, in other words. We skipped that step of writing it like that. The top would be the square root of 10, but how does that help me on the bottom? Well, the square root and 5 squared are inverses, so this just leaves you with the square root of 10 over plain old 5. Now it's simplified because there's no radicals in the denominator. But how does that work now when we're dealing with fourth roots or cube roots like you see on your screen? So I begin the same way by making this the fourth root of 7 over the fourth root of 8. Now, 8 is equivalent to 2 to the third power, okay? So you could do factor tree if you need to. So I've got the fourth root of 7 over the fourth root of 2 to the third. Now, if it were 2 to the fourth on the bottom, I would be able to take the fourth root of it. So this time to rationalize, I'm going to multiply top and bottom by the fourth root of just 2. Why? So that in the denominator, I get the fourth root of 2 to the fourth. Right? Keep your base and add those exponents. Numerator would be the fourth root of 7 times 2 would be 14. The whole point of this is so that the bottom, they undo each other and it leaves me with just this base of 2. So I have the fourth root of 14 all over regular 2. Don't make the mistake of dividing the 14 and the 2. One's under a radical, one's not. Can't be done. Okay, so let's check out 10. So 10's got variables. We're assuming again that these are positive variables, so we don't have to deal with any weird conditions. Cube root of y over cube root of w to the 7th. Now, think about when I do exponent divided by index. That would be the same as w to the 7/3. Well, I would want it to be a multiple of 3. Like if it were w to the 9/3, then I can take the exponent divided by the index. So if I multiply, let's see, top and bottom by what power of w would work? Well, I'm going to make it 2 so that I keep the base and add the exponents. And again, this here is a disguised form of 1, so this is legal. So what do I get in the numerator? I get the cube root of y times w squared all over. In the denominator, I would have the cube root of w2, keep your base, add your exponents, w to the 9th. And again, y. Is that helpful? Because that's the same as w to the 9/3, which is just w to the 3rd. Right? So I have final answer, cube root of y times w squared over w cubed. Simplified because I've got no radicals in my denominator. Lastly, I don't want you to forget about your rational exponents. So you're going to practice using your rules, mixing together all our rules from this course. So this is held by division. So what do? Keep my base, and I take my top exponent minus my bottom. So 1 minus 1/3 would be 2/3. Easy peasy. Next one, number 12. I got power to power. I'm going to begin by distributing this outer exponent, which would be 27 to the 1/3, which is the cube root of 27, and the cube root of 27 is 3, because think of it, 3 times 3 times 3 is 27. So I get 3, keep my base, and multiply. 3 times 1/3 is 1, so p to the first. Q to the 12 times 1/3 is 4. Beautiful. Look how easy that one is. All right, 13. This one, here's what I noticed. This time I have a 1/3, a 1/3. They've got the same exponent, so here's what I can do here. I can make this 42 over 6 raised to the 1/3, and then that's raised to the second. Why would I do that? Because I can divide 42 by 6, that's 7, and then power to a power would be 1/3 times 2 is 2/3. So it's 7 to the 2/3. Isn't math awesome how you can just apply these rules and you take these ugly, complicated expressions and they get so easy? All right, 14 and 2. We're going to divide our coefficients the way they always have. We don't use any special rules there. 14 divided by 2 is 7. Move on to your variables. I have an x to the first and an x to the 3/4. So the rule would be keep your base and take the top exponent minus the bottom. 1 minus 3/4 is 1/4. The y to the 1/3 has no like base, so it stays where it's at, and z to the -6 moves up to the numerator so that my exponent becomes positive. And there we go. Nothing else to do there. 7 to the 1/4 times 7 to the half. Keep your base, and we're going to add our exponents, so that's 7 to the 3/4. Amazing. 16. Let's see here. Well, I have 16x to the 1/2. These are almost like terms, but since my base is more than one thing, I'm going to first do 16 to the 1/2 would be 4, because that's the square root of 16. X to the 1/2. And out here I have negative 3x to the 1/2, and this is addition. By doing that, I created like terms. I got this x to the 1/2, so I just combine my coefficients and get 1x to the 1/2, which is just the square root of x. But you can leave it in rational exponent form. I was just showing that. All right, time for you to practice.